Okay, I guess we're getting ready to start. Okay, let's start out. First of all, any questions about anything logistically? Today the homework 4 is due. It is like any other homework. For those of you who haven't used an extension, if you want to use it on this, that is of course fine. I'm going to give it another minute or two, but I do want to find out how fast people's fastest programs are. So I do want to collect some for the thing. Yes?
Should we email our code to you even if we don't think we're in the top 5?
Okay, I only want to talk to the people who are in the top 5. So maybe now let's take a look at this thing. How many people's programs in here were able to do all cases, let's say up to 15? Okay, a lot of 15 MERS. Okay, how many people were able to do up to 20? Okay, if I count hands, I am seeing 1, 2, 3 hands for 20. So what I'm going to say is anybody who can do 20 or more, okay, I want you to email me your program, okay, in a way that I am likely to be able to compile it and run it, okay? That means, instructions, that means something like that. So that says 20 or more, yes? Well, let's take a look. The people who raised their hands, how many got 20 in all cases? I am seeing 2 20s in all cases. How many were 20s in one case? Okay, I'm now seeing a few more. I want all the people who did 20 in all cases and anybody who's brave who did 20 in some cases. Okay? So you got to decide if you did 20 by cheating or if you think you got the real McCoy. Okay, I want 5-ish. I'm seeing 3 that say they did 20 at all. They may be lying. We'll discover this. Okay? But if you think you were at 20 or close to it, send me your programs. Yes? Like I said, we're going to run these. We will decide who the winner is. Okay? So you guys decide if you think you are in contention. You should send it to me, okay? So by that I mean, so anybody who was able to do 20, okay, with some level of confidence, mail me your program, yes?
So is it safe to say that any type of heuristic you did, because some of the graphs were like, they were just trees, and some of them were other situations, so any heuristic you used would only have worked on one of those kinds?
Okay, so let's think what you're saying here. What you are observing here is that the performance of the program is going to be differing on different kinds of inputs. Okay, that's very much true. You're saying that my program algorithm is only going to work well on one of them, or any heuristic is only going to work well on one of them. If you have a robust enough heuristic, it should be helpful on a variety of different cases. So if your heuristic was see if it's a complete graph and then say, aha, that's not robust. If you're having something that says, here is a high-degree vertex, or here's a collection of high-degree vertices, maybe I can do some pruning based on that. That is robust, okay? And so that's the distinction I would make. Certain examples are going to be easier than others for reasons other than just the gross size of the problem, just because of the structure of it, okay? So if you can do 20, I want to see your program mailed to me. Okay? Okay? If you can't do 20, that's fine. I want to see your printout there. If you can do 20, I also want to see your printout there. Okay? Any questions? And so from the people who could do 20 comfortably, those are the ones that I would like to see submit me their codes. And we will decide who the winner is. Yes? You should send me enough that I can mail it to a TA that they can figure it out and get it running, okay? And you have to decide what that means. Historically, a certain number of these we can't get running, and they don't, so the more you can do to make it run by explaining how to do it and do, if possible, do something less Baroque, that would be good, okay? Any questions here? But I look forward to that, and we will decide who the winner is. Any questions about that? The midterm is, I believe, a week from today. Is that consistent with what everybody knows? Okay, so it will be a week from today. 1/3 of the class is going to have be exiled to a different classroom, just like it was at this previous one. Presumably the midterm right after the cutoff, the bunch right after the cutoff from last time. I will put that on the web and we'll announce the details next class. But some of you should be prepared to take it in another room. Any questions? What will it cover? It will cover graph algorithms. It will cover backtracking. It will cover dynamic programming. Okay, it will have 5-ish problems, okay, just like the other one. A large hunk of those problems are going to be verbatim from the book, okay, but I don't guarantee all of them. Okay? Any questions? I don't guarantee what fraction other than, I'm going to be looking there. Any questions? Okay, so how do you study? Again, I recommend homeworks. One thing that I will do is I will post the last homework, okay, which is going to be about which will include dynamic programming problems. This will be due after break, but so you get some idea so you can start working on some dynamic programming problems. Somebody send me mail to remind me to do that as soon as I get to my office, okay? Yeah. Answer to homework 3 will be posted, I believe, when I get back to my office, so remind me of that. And homework 3s themselves, I am told, will be back next class. Okay? They're not here now. Any questions? Okay? Any other questions about the exam? Okay. So let's go and start to talk a little bit more about dynamic programming. Where were we? Again, dynamic programming. What is dynamic programming? It is solving, it is a way of solving recurrence relations efficiently by storing partial results. It is a question of the key idea here is that we want to take a look at our problem and come up with a recursive, what is the approach? The way I think about how you solve these things, I think of a function that if I knew how to compute would tell me the answer. I come up with a recurrence relation to solve that function. And then I prove that I can evaluate that recurrence efficiently because I can store partial results. That is my 3-pronged game plan here. Any questions? So let's look at the problem of the day. We'll go back to, I think, string matching a little later. But just to talk about the problem of the day, this, I believe, was the problem of the day. I believe I'm right. Okay? And it says that a certain string language allows a programmer to break a string into 2 pieces. Okay? This involves copying the strings. So it takes n units of time to break a string of n characters into 2 pieces. Suppose we want to break a string into many pieces. The order in which the breaks are made will affect the time that is used. So let's take a look at this example here. Let's see, Kachunk, I think it's draw a pen. Now go away. Here I have a string that is 20 characters long. Suppose I had a break at 3 characters, 8 characters, and 10 characters. In the end, I want to end up with a piece that is of length 3, a piece that is of length 5, a piece that is of length 2, and a piece that is of length 10. Does everybody see? That's what I would like to do. And what I am allowed to do is to execute a chop string at a position statement, which will cost length proportional of the string and give me 2 pieces. Okay? So recognize that there's different ways that I can chop this thing into pieces. What's the cost if I cut this thing from left to right? Okay? If I cut it from left to right after the first cut, I've got 3 and 17, right? And the cost of that would be 20, because that was the length of my string, right? If I cut the next piece at 8, what would the cost of that be? Then now I'm going to have something here that is 5 and 12. What would the cost of that be? What was the cost of that cut? 17. And then I have one more cut to make, okay? Which is I cut it at 10 and I get 2 and 10, right? 2 and 10, that would cost me how much? 12. Does everybody agree that the left to right strategy, the cost of doing that would be what? 49. Does everybody agree with that? Do I get a different cost if I cut it from right to left? Let's think about that. If I cut it from right to left, what would my strategy be? I would pay 20 and I would get 10 and 10. That would have been my first cut, right? My second cut would have got 2. The cost of this would have been what? Okay, I would have ended up with 8 and 2. That would have cost 10, right? And the last piece, which would have been 8, I would have cut that into something of 3 and 5, and that would have cost 8. Does everybody see that right to left is a cost of 38, where left to right was a cost of 49? Okay? So one way of doing it was better than the other. This is important to see. If not, the whole problem has no meaning. Okay? Does everybody see that that one way is better than the other? And in fact, there's a third way of doing it. I could have chopped it right at the 8 first, and then done something on each side, which would have a different cost to it, right? In general, the sequence of cuts that I'm going to be doing is a permutation, if you want to think of it, right? The cuts, if I'm doing one cut at a time, I'm basically going to be giving you an ordering of the cuts. There are, in fact, n factorial possible ways to do this cutting, okay, if I have n cut sites. Does everybody see that? Some of which are going to be more expensive than other, at least one of which is the cheapest. The goal here is to find the cheapest way to cut it, okay? Any questions about what the problem is? Okay, do people see that there are a lot of possibilities as you have a lot of different cut sites? Do people see that there is a different, there is a different, that different cuts, different orderings give wildly different costs, okay? And so finding the cheapest one may very well pay off if we can figure out how to do it algorithmically. Any questions about that? Okay? So that's what the problem is. I basically, the problem here is, give an algorithm that given a list of character positions after which to break, determines the cheapest way to break it in n cubed time. Okay? The cheapest sequence of cuts to break it in. Okay? Any ideas how we might do this? Okay? Yes?
Well, we can think of the problem differently. We can think of it as adding together sequences of already broken strings. And so when we concatenate two string bits, two string partitions, the result costs the sum of the string length.
You want to say, instead of thinking of it as from top down, here I have this big piece of wood. What order do I chop it in? You could think of the little elementary pieces, how do I stick them back together to make the wood? So there is a top-down or a bottom-up way to look at it. Are they any different when I look at them that way? It's not clear to me whether there is or is not. Okay, but we agree that that's two different ways you can look at it. Any ideas of an algorithm how to cut this? If you're now asked to do this, what do you do? Yeah.
I would try to find the cut position that's as close to the middle of the string as possible and cut it as nearly in half as I can manage.
Okay, so what he's saying here is that he has observed that this was a good thing. Okay?
I can't prove that that's the best result, unfortunately.
Okay? His idea said, look, cutting it in the middle was a good thing because the pieces that I had left were going to be, were going to be smaller, and so any subsequent cut is going to be cheap. That's kind of what he's trying to say, right? So maybe an argument is always cut near the middle, and that might be a good heuristic, but unless you have an argument that that's the right way to do it, okay, it's not clear to me that that is the right way to do it. So for example, suppose, let's say, that there are a zillion little cuts. Now let's say we had the following situation where there were a zillion little cuts here. Okay? Your strategy would be cut it in the middle, right? Perhaps a better strategy would be haul off this piece, haul off this piece, and now do all your subsequent cuts on a very, very small piece. Right? It's not obvious to me. I don't know if I have a real counterexample here, but I see no reason to believe. I believe cutting it in the middle looks better to me usually than cutting it at the end. But I think it depends upon where the other sites are. And if you're going to try to do something like that, you'd better have a proof. Or else you just say, I got a heuristic. Okay? Which will suffice for many bosses, just not for me. Okay? Any questions? Now let's think if there's an algorithm. The other possibility, yeah. So what would be another way to look at this? Okay, I would want to look at it with dynamic programming. Okay, and so how do I think of this problem as dynamic programming? Maybe we'll go to the board here. Okay. What I want to do is to think of, can I define a function that if I could compute it, would tell me the answer. Okay, does everybody see what my problem is? We don't have this, but we do have our string. We have bop, 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 a sequence of cuts on something of length. We've got the length of the thing. We've got n cuts. Okay, is there something that you could tell me, a function you could define that would tell me the answer? Okay, as a special case if I knew how to compute it. Okay? Yes?
Find the code that will shear off the most unused space.
So you're saying here, let's think about what you're saying. If you're thinking, you're going to call this thing, I don't know what we're calling, I don't know what our arguments are yet. But you're going to be telling me, find the cut that minimizes the cost. I don't know if that's what you're saying, or something like this. Okay? So this is not the kind of function that I want to see. Okay? Why is it? I am used to these things. All of these things that we're going to be looking at return costs in general. Okay? As opposed to finding the cut. It's going to return us the cost of something that we want as cheap as possible. Okay? So this is not the flavor quite of what I want it to be. Okay? Yes?
So the way that I saw it was putting strings together. The cost for a string whose left character is at I and whose right character is at J is the minimum. You have a number of breaks between them. So you can choose which break you want to put them together. So I'm doing the bottom-up approach. You can choose which break you want to put them together. And so it's the minimum of CIK.
Okay, no. You're giving me a solution. I don't even want to. I want to know a function that I can write in English that if I could find a recurrence for it would help me. Okay? Yes?
The cost of breaking any particular string is equal to the cost of breaking it at one break site plus the cost of breaking apart the two subsets.
Okay, again, you're giving me a way to do it. What I'm looking for here is I want to know what is the cost of the cheapest way to break up the stick, or the string, I guess it's a string, from position I to position J. Okay? Let's think about whether if I could compute this, this would be interesting. Okay? What is Cij is going to be what is the cost of the cheapest way to break up this string from between position I and position J? If I could compute this, would this tell me the answer that I want? Yes.
Absolutely.
Why? What?
Plug in I equals 1, J equals N.
If we notice that if it's either maybe it's 0 to n or something like that, okay? But does everybody see that if I know how to compute this for any I and j, I know how to compute it for the whole stick, right? By just giving it the whole stick, okay? So I have made progress here. I have defined a function, okay, which if I had the solution of this thing, a way to compute this for any I and j, the I and j that I care about is, is an instance of that. How many people see what I mean here? I haven't done any recurrence yet. It's just definition. Does everybody see how this definition is potentially a step in the right way? Yes?
So when you say break up the string from I and j, you mean include all of the cuts?
Do all the cutting, complete the job, okay? So that I, atomize this thing into sticks, so that I go from this to ka-chunk, 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 okay? It's not one cut, but all the cuts, right? So maybe I didn't have this clear enough. Again, I got to work on the English before I work the total cost. Total cost of the cheapest way to break up the string, right? Now is it clear? Okay. Any questions? Any questions about this? If you don't see this, why is this progress? Okay. Any questions? You look at me suspiciously, so if you have a question, I'd like you to know. I haven't done anything yet, except for I've done a couple of things. Okay, this is why we're going through it. What have I done? First of all, I now know that if I can come up with a recurrence relation to compute this, I am done. Right? I may not have a recurrence relation to compute it, in which case it's lost effort. Right? I also know if I come up with a recurrence relation for this, it will be an efficient solution. Why? How big a table am I going to need for this thing? This value is going to go between 1 and n, 0 and n. This value is going to go in n, right? So there's going to be like n squared table entries. Okay? So I know that the state of my recurrence is small, if I can define a recurrence like that. And I know that if I could do this, I have solved my problem. That's progress. Okay? It's not the progress we don't want to stop here, okay? But it's progress. Any questions? The other thing is I now have a name for this thing, okay? Now that I have a name for it, I can now write a recursive program. If I don't have a name for it, I can't make a recursive function out of it, right? Now, give me a recurrence for it. What would be a recurrence relation to compute this thing? Okay? Yes?
Let's say there are so many breaks within that set. So you talk about, are you saying C0n or Cij?
That was just an example of a special case, right?
So then let's say there's a break at k, so you take the minimum of...
The min... as k goes from
k in our set of breaks.
The breaks between I and j, right?
Yeah.
For all, we may want to let k be the breaks of what?
Of Cik.
Yeah.
Plus Ck plus 1j.
K, actually, is it k or k plus 1? When you chop it, you still have the p. He's saying that if I chop it here at spot k, what you're really saying is from I to k is a subproblem that has to get solved. What's the other subproblem? Is it from k plus 1 or is it from k to j?
It depends on whether it's inclusive or not. Are you saying I to k inclusive or
No. The way I think about it is a point in the thing to be cut. Okay? Okay, I'm going to say, let's just put it, the indices are sometimes a little tricky here. But basically, what is he saying before we get the detail gone? He is saying, once you cut it at the kth spot, what is the total cost? There is the cost on the stuff that you're eventually going to have to do left of the kth spot. There is the cost of what you're going to have to do to the right of the kth spot. And
then you add the length of j and I.
the length from j to I, which I think we're going to use by this notion, j minus I, which is going to be the string length.
That can be outside the minimum.
Okay? So let's look at this equation now and see if this makes any sense. Okay? Does everybody see now what the idea of what he's trying to do here is? We have a function that for any I and j will tell us the cheapest way of dealing with that substick, right? You're coming along with your axe, and you got to cut it someplace. If you want to do this thing between I and j, you're going to make a first cut. That first cut chung is going to be someplace, some k. The cost of doing that is, regardless of where you cut it, you pay the string length as a cost for making that cut, right? But now you've got two subproblems. The stuff to the left of the cut and the stuff to the right of the cut, right? And to finish the job, you've got to solve this problem, okay? Does this recurrence make sense? Who does this recurrence make sense to? Raise your hand. Who does this recurrence not make sense to? A question like, I don't see it, is a good question. Any questions about that? Okay? But now we have a recursive formula to compute this thing, right? Does everybody kind of see that? Are there base cases for this recurrence? Yeah?
I would argue that the base case is when there's no cut sites in between I and j.
Okay, so there are a couple of different ways to have defined what my input was. Was my index over the cut sites or over the actual positions? Okay? But what I think it's pretty clear that the cost of cutting from I to j is going to be equal to 0 if there exist no cuts between I and j. Does everybody see that? Okay. If these indices were actually representing the cut sites instead of the positions on the integer line, which is probably a little bit better, that would mean in that case CI I would be equal to 0. That if you already have something where there is, or CI comp plus 1 would be equal to 0, right? When you've got it where you've got something where there is no cut site between it. Okay? Does everybody see that this is basically the recurrence that says when the thing is completely cut up, the basis case, when a piece has no cut site in it, we are done, and it costs us nothing at that point. That's what this is really saying, right? In general, we're going to pick which cuts first? The cut that minimizes the total cost. The cost of what work we will have left on the left and what work we have left on the right, considering that we had to pay this regardless of where we did it. So this could be factored out of the min and put over here if we want, okay? Because it's not going to affect the choice of k. Any questions? How many people see this recurrence? Okay, any questions about it? Now, what is the complexity of this algorithm? Okay, let's think about it. How do we analyze the complexity of a dynamic programming algorithm? What is the magic formula? The number of boxes times the cost per box, right? How many boxes does this thing have? Okay, somebody else. How many boxes? N squared boxes. And how much time does it take to compute each box? N, because you've got this thing, right? Now we're minimizing over all possible choices between I and j. I and j could be from 1 to n, right? So there's n possible choices where this thing is already sitting in memory, where this thing is sitting in memory, where this is the subtraction of two integers, right? Does everybody see that once we have a k, it takes constant time to compute this, but we have to try all potentially n possible k's, right? So my analysis is this is n times the n squared boxes. Okay, n squared boxes times n time at most n steps per box This is an n cubed algorithm. How many people see why it is n cubed? Any questions about it? Yes? Why is it n squared box? Because a box has a starting point and an ending point. Okay? If n is the number of possible cuts on the line, we're going to have to work this out for every possible pair of starting and ending points of the n cut sites. There are n choose 2, which is n squared, big O of n squared, possible pairs like that. That's why it's n squared. Does that answer that? Any questions? Okay? So the way I think about it is I have my formula. Once I have my arguments, how many choices are there of this? There are n. How many choices of that? There are n. N times n is my number of possibilities. Any questions? Okay? Any questions about this example? Okay? Okay? Because again, this has the same basic paradigm that we're going to be doing over and over again. Okay? We define a function in English that, if we could compute it, would tell us what we want to know. That's my first step. Then I will design a recurrence that will compute this function, okay, including my basis cases. And then I will analyze it by saying, okay, because I know how many possible arguments there are and what the maximum time it takes to compute any one of these, the product of those two gives me a complexity of the algorithm. Any questions? Okay. Any questions about this? Now, there is, recognize, the thing to note here that is a little bit confusing. Again, there's one reason why this is confusing to people sometimes is it seems like there's a lot of moving parts, okay? That there's a recurrence and there's a table and there's, okay? But look what is sort of kind of clear. It should be clear that if the distances here between this and this are smaller than the distances from between here on the right side are smaller than the distance on the left side, then that means we can start by computing the distances for all of the very, very small distances, size 1. And then the ones that are size 2 are going to be made up of pieces of size 1. And the ones that are of size 3 are going to be made up of pieces of size 1 and size 2. And the pieces of size 4 are going to be made up of pieces of size 1 and 2 and 3 and 4. See that there is a way to evaluate this recurrence from sort of the smallest parts to get bigger parts. And we're going to keep getting bigger and bigger things. That's the evaluation order. That's the table manipulation and the loops and things that go on. And once you see that we always have bigger things always depend upon smaller things, we can fill in the table from smallest pieces to biggest pieces. Okay? And the pieces we need will always be there. Okay? Any questions about that? I don't know if that's helpful or not. Any questions? Okay? Really the hard part, the creative part, comes in defining your function and defining your recurrence relation. Okay? Any questions? Any questions about this one? Okay. So let's look at, let's go back to, let me think how I want to do this. Actually, I am going to, since we've been doing some design, let's go back and, let's come back here. Excuse me, escape. Get rid of this one, ka-chunk. Ka-chunk. Let's go back to where we were, view. Actually, while we're on the design, let's do another design example. View, full screen. Kabang. Let me show you let's look at another one from scratch before I show you some other that it's not really, you didn't have to do it from scratch. But let's look at this one from scratch again. What we are saying, okay, a numerical sequence, okay, is monotonically increasing. If every element is, if the ith element is at least as big as the one before it, okay? So numbers that are in sorted order are monotonically increasing, okay? Suppose I give you a permutation of numbers or a set of numbers like this, okay? Suppose I just want to find what is the largest subsequence, the largest subset of these numbers, that if you deleted everything else, what was left was in sorted order. Okay? Looking at this thing, are there some numbers here that if we deleted some digits here, that if we deleted some of the other ones, what got left was in sorted order? Okay, can somebody tell me which ones I could keep to leave them in sorted order? Okay, make me a proposal. Yes. Yes, okay, I want a proposal. It doesn't have to be the best one, yeah. He's saying if I delete 3 and 1, what's left is 2 to 4 to 5 to 7 to 9. Does everybody agree that if I delete those 4 numbers, I get 5 numbers that are left that are in sorted order? Right? Okay? So you could imagine something that I want to, let's say that I wanted to show off this class to somebody. I had a visitor coming in. President Stanley came in. I want to make a good impression. I'd line you guys up against a wall. And I'd want you guys organized by height so he saw it pretty good. And what I could do is tell anybody who's not in, I'd like to find the smallest number of students I have to tell to leave so that everybody else is in sorted order. Okay, that's the problem that I'm asking for. Okay, any questions? Okay, there are reasons why you might want to compute these things. This is often let's say that, let's say things should in principle be in sorted order, but sometimes there's a couple of mistakes. Finding what is the smallest number of mistakes to correct would be exactly what this problem is. Okay, if you want to think about why might this ever come up. But let's think what my problem is. My problem is I'm giving you a set of numbers, okay, a sequence of numbers, and I want you to delete the smallest number of elements, okay, or keep the largest number of elements, such that those elements are sorted. Okay? Any questions about that? Can anybody, how would we go use dynamic programming to try to solve this problem? Okay? Any question about what how many people understand the problem? It may be still a little too abstract. How many people don't understand the problem? You can admit it without fear. Okay? How can we go about doing this one? Okay? Let's now do this one by dynamic programming the same way I was telling you I did the other homework, or the problem of the day. What is the first step we need to do? Yes? I need a function. What should I call my function? Okay? Give me a letter. This is a letter of the alphabet. That's easy, right? Okay? But what function is it that I should be computing that would be helpful? Yeah?
The number of elements you need to remove between I and j so that ij is a monotone subsequence.
Okay, so what you want to say here is C sub ij is going to be equal to the min number of elements to remove from, between the ith element, right, and the jth element to leave a sorted sequence, right? Does everybody understand what function here is defined? Okay, or do I need to go to the board for this? Maybe it's not possible to read what I did. Never really possible to read what I do, but it's maybe more profound when I do it on the screen. Any questions? Who here wants me to go to the blackboard? Who here wants me to stay at the screen? Nobody. Okay. So let's go to the board here. And let's think about this and see if this is a good start or not. Okay? Here our problem is this, we're given the permutation. We want to find the smallest number of elements to drop. He gave me this function here. Cij is going to be equal to the min number of elements to delete to leave a sorted sequence between I and j. Is that right? He's going to specify an I here. He's going to specify a j here. And say, what is the smallest number of elements to delete between here to leave a sorted sequence? In this particular case, what's the smallest number? We have here a 35176. What's the smallest number he has to delete? He can delete to leave a sorted sequence. I think he can delete two of them, right? Which two? He could delete the 1 and the 6 or the 1 and the 7. Right? Does everybody agree with that? Two ways to do it. Okay, let's think if he's made progress here. If he knows how to compute this thing, does he would this help solve our problem? Okay, how would we solve our problem if we knew how to compute this? Yeah? Right, from the first element in the matrix, in the permutation to the last element, right? So we know that, in fact, if we could compute this thing, it would be good, right? Now, let's think if we can compute this, okay? Can we come up with a recurrence for this? Okay? Let's think about it. Actually, it's not the way I usually do it, so let's think if we can come up with a recurrence for it. Okay? Well, let's just think about it, okay? Is there a recurrence here that would do what we want to compute this? Okay, let me just think for a second. Does anybody have a recurrence? I don't, it's not quite natural. Okay, is there a recursive way to think about it? It's the way we thought about the other one doesn't sound right, does it? Okay? Because if we broke it at some point, okay, it's not clear how to combine it, right? Although maybe it is. Okay, let's think about it here. Under what condition could I combine it? I'd like to take some element k and decide whether I could combine it or not. I'm not really seeing a recurrence here. Okay? Give me 1 second, but then let's see if there's another definition that might lead to it. Okay? Any questions? So this doesn't look like it's good. He's gotten some part of the way, but he hasn't gotten a recurrence for it. Okay? Let's see if we can come up with an alternate recurrence that might do this. Okay? What might be an interesting recurrence? Okay? I'm now going to define one, I think. Let's let C sub I equal the length of the longest subsequence ending at the ith spot. Okay? Let's think about this. This may be a little bit of a leap here, but let's think if this function would do what we want. Okay? Suppose I knew the length of the longest subsequence, sorted subsequence, ending at each spot. Okay? What is the length? Let's clear this just because I can't erase it with the other one. Kabunk, kabunk, clear ink. What is the length of the longest subsequence ending at this position? 1, right? It's just at 2, right? What's the length of the longest increasing subsequence ending at this position? 2. What's the length of the longest one here? 2, right? What about this one? 3. Why is it 3? Anybody tell me why it's 3? Why is it 3?
Because the length of the longest subsequence at the previous position, I minus 1, was 2, and we could add the element at position I to the end of the sorted.
Does everybody see that the reason this is 3 is because this was 2, and you could stick the 5 at the end of this sequence and make it 3. That's why it was 3, right? Let's go on here. 1. What's the length of the longest subsequence ending here? Okay. I hear 1. Okay, ending at, I want to say, exactly the ith spot. Okay? In this case, it would be, does everybody agree that would be 1? Right? Does everybody, people see why it's 1? Okay, any questions? Like, I don't see why it's...
So it has to include the value at
Has to include it to end at it, right? Okay. What about the next one? 7. What's this one going to be? What's the length of this one going to be? 4. And why is it 4? Because there's 1 here of length 3, and because this ended at 5, this one we know can extend it. Does everybody see that? Because 7 has to be bigger than 5. If this ended at 5, then darn it, this one can get bigger. Does everybody see that? What about the next one? What's the longest one ending at 6? 4. And why is it 4? It's 4 because it can't extend this one, but it can extend that one, right? So what are the rest of them if we understand the pattern? What is this one going to be? 5. And what's this one going to be? 5. It's not 6 because this one can't extend. We know that it ended there, right? So now there is seemingly a recursive-like idea here, right? The length of the sequence at any position depended upon what we knew from the previous positions, right? Now can anybody, any questions about that? Do you see how that table got computed? Now give me a recurrence relation for how to compute CI. Okay, yes?
Get that list of numbers and store however, and you have 2 that are equal in the same one after the other, such as the 2s, the 4s, and the 5s, so you remove one of them.
You're saying when I have something, remove something. That's not the language I can talk. I need a recurrence relation depending upon C, right? So I need, in some sense, a formula that's going to be in the language of C. Any ideas of what I can compute? Yes. Let's say you want to say, I know, so K equals from 1 to I minus 1 of what? Of CK. Okay, it's a max of this, and you want to say, okay, the max of this over all K from that to 1, where such that, okay, P sub K is less than P sub I. Let's say that we've got, this is our permutation is named P. We need a language for it, right? What is she saying here? She's saying, suppose this is a permutation, and this element is P sub 1, 2, 3, 4, 5, dot, dot, dot. She's saying I want to maximize over all possible predecessors of my element, right? All possible indices that are to the left of me, that's what k is, where the kth element is less than the ith element. If so, then I can take the ith element and tack it on here to make a longer sequence, right? This is now almost right. What is the one thing that is wrong? Plus 1. Okay, let's think about this now. Okay, does this compute what I want it to be? Okay. Oh, first of all, let's just ask a question. How did we find, given this value, CI? If I had CI, does this tell us the answer to what the longest overall sequence is? If I knew how to compute CI? Then that would be what? My ultimate answer is I want to take the max of CI as I goes from 1 to n, right? So this function, it should be clear, is good enough that it would tell me the answer of what I wanted. If I knew how to compute this, I could solve to find the length of the longest sequence, right? And this recurrence is going to tell me how to do it. It's going to be the max over all previous positions, okay, of if that previous position is kosher, in that the element that ended that sequence, p sub k, is less than the ith element. Then the ith element can extend the sequence, right? And we want to pick the kth element such that the length we get by extending it by this one element is bigger than any other possibility. Okay? How many people understand this recurrence? How many people don't understand the recurrence? Okay, a couple of people. Good. Okay, boldness here. What is it doing? Note that this is doing exactly what we were doing before. Let's go back here, ka-chunk, ka-chunk. Let's go back to this one over here. What was the length of this element? What was the longest sequence ending at the 4th position? Okay, that included that 5. How long was it? 3. Why was it 3? Because if there was a sequence of length 3, it was going to have a sequence of length 2 ahead of it that ended on a smaller number than 5. Does everybody see that? And it could have been this one, or it could have been this one, right? K equals 2 would have worked, K equals 3 would have worked. This is exactly the thought process we're going through. What is the sequence that ends here? I guess we need a basis case, right? What's our basis case going to be? Okay, you want to say if no p, that's not really a basis case. What would be a basis case here? I was going to say, the way I would like it, what about C0 equals 0? Okay? And now what we're going to be saying here is, again, it's a different way. Suppose, let's say that C of 0 was equal, we start out with a minus infinity here, let's say, or something like that, right? Then or basically it's a cost of 0 plus the 1 here. I want to be able to make it so that 0 plus 1 is 1, right? So this is basically going to be the basis case. What about here? I want to find what is the smallest, the largest number here that ends on a number that is less than 7. In this case, it's easy. It's got to be 4. Okay? For 8, it was more interesting. The 8, this was 5. This was 4, I believe. Am I right about that? No, yeah. So how could I do it? There was a bigger thing that ended here, but my number here is smaller than the ending point there. So I couldn't extend that one. But I could extend either of these to get a 5. Any questions about the recurrence? Yes?
So the plus 1 is there just to increase the number, like the amount in the sequence after you found one that
Yes, my sequence is going to be one longer than this guy's sequence because I'm at the end of it, right? That's where the 1 is coming from, right? Exactly right. Any questions about that? What is question?
So I think this means that our answer might not necessarily be at Cn. It could be anywhere in the array.
Right. So what she also said is that the maximum, if let's say we want, this function is not giving me exactly the answer that I want. What I really want, my answer, is going to be equal to the max of Ci as I equals from 1 to n. Does everybody see this? The maximum longest sequence is going to end someplace. It is going to end at some position I. And the length of that longest sequence is going to be Ci. Okay? So this is what it takes to actually find the answer that I want. But C is the dirty work that I need to do to find that out. Okay? Yes? Yeah. Let's say yes. Okay? And so you're right here. Okay? When you program these things, the only thing you get wrong is the basis cases and the indices. You're always off by 1 when you program it. Okay? For just that reason. But the basic idea here should be clear. The detail of, is it I minus 1? You've been there. Okay? Any questions about it? What is the complexity of this algorithm? Okay? How do we figure out what the time complexity of this algorithm is? Yes? Number of boxes times the cost per box. How many boxes do we have? N. N plus 1, which is n. Okay? So we've got n boxes. How much time does it take to fill in each box? So what's the total complexity of computing all of these CIs? O of n squared. Plus we have to do this final bit of dirty work here, right? How much time did this take? N. What's n plus n squared? N squared. This gives us an n squared algorithm for doing that. Okay? Any questions about that? Okay? So here the cleverness was in exactly the part that you told me was not good last time, when you said we didn't make any progress. The key here is writing down the right English sentence for what you compute that would help you. Okay? And again, the one that he gave first had the property that it would have helped, but it wasn't computable. The key is we need to have something that will help that is computable. Okay? And then everything follows nicely. Sometimes you have to try a couple of different formulations, but that's really part of the design work here. Any questions? Okay? I will encourage you. I'm now going to go talk a little bit more about the mechanics of this in a little lower level. What I do encourage, I don't think I'm going to have time to talk about, I'm going to go back now and talk more about string matching and edit distance. And just to look at that on a more detailed level. What's interesting is that problem I just told you about monotone sequences falls out as a special case of edit distance, which is also n squared if you think about it. You have two strings of length n, that's also n squared. So you might want to look at that just to get a better sense when you read in the book. But let's talk again about edit distance. What was edit distance? Edit distance was, as we talked about, going to be taking two strings, what is the cost of turning this string S into this string T? And our cost basically was the cost of turning the first I characters of S into the first j characters of T, and what was the recurrence? It was the min over all possible ways of ending it. See, I minus 1, j minus 1, plus the cost of, did that last thing match? Sub I, j. Or it was C sub I, j minus 1 plus 1 because it ended on a deletion. Or it was C of I minus 1j because it ended on an insertion. Right? This was the idea that we had last time. And that, in general, to compute the ijth value, we needed to know how we ended. And there were three possible ways to end. We could end on a substitution or a match. We could end on an insertion. We could end on a deletion. Okay? And so long as we had these three values in there, that was what we needed to do. Any questions about that? Okay? Any questions about this edit distance recurrence? I'd like to go carefully through now, well, not carefully, but I want to go talk a little bit about some of the other mechanics of this issue. Let's first look at the issue of evaluation order. Okay? Let's say what should be clear, and if it's not, I want to hear rebellion. To evaluate this edit distance thing, we have this idea that every cell in our matrix corresponds to a prefix of the cost of editing a prefix of one of these strings into a prefix of the other strings. That's what each cell in the matrix is, right? It should be clear that in general, each cell depends upon only three other cells in the matrix, right? And that they happen to be located exactly where I have them. Right above me, right to the left of me, and diagonally above me. Okay? Any questions about that? These elements, the cost of editing the empty string into everything, this was a initialization condition, right? The cost of editing everything into the empty string, this was an initialization condition. Okay? Does everybody see that? Now, given the fact that we can fill in a cell whenever we have the three neighbors, in what order can we fill this thing in? Let's think about it. Yeah?
I would start the cell that's at, I guess, the upper left-hand corner.
Does everybody see that this cell over here has its three buddies? Right?
Then I would proceed to the right, and then...
If you want to proceed to the right, this guy now has its three buddies, right? This guy also has its three buddies. Does everybody see that if we fill it in along that row, we can continue?
So I guess I would do the rest of them typewriter style.
So you could do it typewriter style or eat corn style, right? Okay? That would be acceptable, right? Okay? Is there anybody else, though, we could do at this point? Let's think about it. Is there any other way of doing it? Okay? Is there any other cell we know enough to fill in now? Or are we doomed to fill in this guy? Is there any other cell in this matrix that we have its three buddies ready for? This guy I could fill in now, right? Does everybody see that? This guy I can fill in now, right? I could fill in this guy if I want. Now which ones can I do? Okay? I could do this one if I want. I could do that one if I want. I could do this one if I want. Does everybody see that? So there are a lot of potential orders in which I could fill this matrix in, okay, with the property that the next guy is waiting there. Okay? That much I want to kind of be seen. The most obvious orders for doing it are, as we said, typewriter style or corn style, where we go along like this. Is there anybody who eats their corn by spinning the cob around and then moving over to the right? If you eat your corn in that kind of a perverted way, you would be filling it in like this. Does everybody see that? Okay? That's a rotational way of thinking about it. Some people may even eat, okay? There's some people who are really cockeyed, I guess. They might eat their corn diagonally, okay? I haven't thought about this too deeply. But you could have actually filled in your matrix going in diagonally as well. Does everybody see that if we filled it in like this? The cells that we want are all there. Does everybody see that? Okay? So there are potentially many orders in which you could fill the matrix up, where the elements you want are already there. Okay? Now, which is best? Doesn't make any difference. One might say the easiest way to program it, okay, which is usually going to be, I would say in this case, I would probably say typewriter style, or, column-wise style, right? Any questions? Actually, you want to know all the different ways of doing it, just to tie things together. What if we view this thing as a DAG, okay, where for every cell, we have an edge from the 3 cells it depends on. Does everybody see that? Every cell depends upon 3 other ones. We could imagine building a graph where we've got n times m vertices and something like 3 edges coming out of each cell, right? If you understand that representation, the interesting thing is any topological sort of that DAG would describe a way in which you could fill this thing in. Does this kind of make sense to anybody? How many people does that make sense to? Okay? So notice that really what we need is, we need this kind of fill-in order. Has got to be acyclic, because if I depend upon you and you depend upon me, nobody can make progress, right? But the evaluation order to fill this matrix in is any such topological sort of that DAG, which is comprehensive but abstract. Usually the way to think of it is you're filling it in from smallest to biggest. Okay? And ultimately we care about the biggest overall. Okay? But logical ways of doing it are along rows of the matrix, along columns, or sometimes along diagonals. There's times when diagonals are actually the right way to think about it. Any questions about that? Okay? Any questions about the fill-in order? What specified the fill-in order in my, in this program? The fill-in order of my dynamic programming thing was specified by these 2 for loops, right? Here I go from 4i goes from 1 to n, 4j goes from 1 to n, basically, right? That's going to fill it in, let's say, along the corn side, along the rows, the typewriter side. How do I get it to go up and down columns? What did I have to do to make it fill it in this order instead of that order? Just swap the order of those 2 loops. Does everybody see that? So the important thing is I have to find an evaluation order where it is already set up. But smallest to biggest is usually the magic answer. Any questions here? Okay, good. One other thing while we're talking about it. Does this thing here, this matrix, this cost matrix, okay, tells me that there was a way of converting this string into that string at a cost of 5. But often we are interested in what the actual path was. Okay? What were the actual changes that happened? If you think back to all the examples we had, all of our recurrences told us the cost of doing something, but they haven't explicitly told us how to do it yet. Right? What was C sub n in the previous one? It was the cost of the way the biggest number of increasing subsequence I could get, right? Or with the problem of the day, it was what was the cheapest cost possible to divide these things. Note that you're not usually just interested in the cost. You want to know how to do it, right? Where do I put my axe to cut that string up? Okay? So how do we figure out what were the decisions made in making that? Does everybody see that we've got a problem? This is the cheapest way of doing it. But we don't know what it matched up to what, just from looking at this value. We know there is a way to turn this into that in 5 changes. We'd like to be able to reconstruct what it is. We know there was a way to cut up the string at a cost of 532. What was the sequence of changes that you needed to make? In order to do that, observe that in our dynamic programming matrix, when we looked at what our dynamic programming was, okay, ka-chunk, ka-chunk, we stored two things at each cell. We stored the cost of getting to that cell, which is the thing driving our decision, but we also stored what was the actual decision that we made to find the cheapest thing. Do you see that every one of the recurrences we look at basically has the form that says blah of blah is equal to the min or max of blah, right? In order to get this value stored, there was some value of k that was picked. That was what told you the decision that realized the right cost, right? So we are going to store what that decision was as the parent. That decision is really going to tell us what was the parent cell that we came from. Okay? Or if you don't like the word parent, in general, it's what decision did we make to find the best one. Then, once we have that, okay, we can then take a look at our dynamic programming matrix at the end, ka-chunk, 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 and say, here I am at this cell. The optimal solution is 5. How did I get here? Oh, the last thing I did was a match. Well, that meant I went back to here, right? Oh, from this cell, what was the last thing I did to get to this cell? Oh, that was a match, right? Does everybody see that at each point, in order to fill in the matrix, we had a value, okay? It made a decision as what was the best choice. If we store what that choice is, we can then work backwards to reconstruct what the right solution was globally. When we made this choice over here, we had no idea whether it would be in the optimal solution at the end or not, right? But when we go back from what proves to be the optimal place, there is going to be a path back in the matrix of where did it come from, where did it come from? And that is what encodes the solution. Any questions about that? This is an important point, okay? The recurrences we have gave us the cost of doing something. The actual decisions we make, we have to store up so we can read them out when we want. So if you look at my innocent dynamic programming thing here, there was, what did I do? I had this line here. Whenever I updated the cost, what was the optimal way to do it? I updated the parent of that cell. If K was the right decision between insert, substitute, or delete, okay, then store that if that was the way that gave me the cheapest cost, so I knew which way I came from before. Okay? Any questions? When it came to my stick thing, remember we had this matrix here, this table. Okay, it was a two-dimensional table for the cheapest way to go from cutting, let's say we remember our stick problem. We wanted to know each cell, the cheapest way to cut between I and J. There was a cost of that. That was going to be stored at this value. But we also knew that there was some value of K that we chose. The parent of this cell is going to be that value K. And once we knew that, then our problem to remain was going to be the cost of IK and KJ. Okay? Any questions about that? So storing the parents enables us to reconstruct our decisions. And reconstructing the decisions enables us to construct the solution as well. Any questions about that? How many people are with me in this one? Okay? So for the problem of edit distance, this reconstructing the solution, is actually, there's actually a slick recursive way of doing it. Okay, and I just want to show you this. How did we reconstruct what the path was? If we want to find what was the optimal solution path after we had filled in our dynamic programming matrix from ending at cell ij, well, we find what the parent of cell ij is. If the parent said it was a match, that meant it went to cell I-1, J-1. That's where it came from. If it ended on an insert, it ended at I-J-1. If it ended at a delete, it ended at I-1, J-1. So knowing which move we had took us to a previous cell. If we want to reconstruct the whole path, recursively reconstruct path says, if I'm ending at ij, my last move is going to be getting to ij. I got there from the previous step. Reconstruct the path that got me to that previous step. Print that out, and then print out me as the last step. Okay? So if you look at this thing, it reconstructs the path recursively. The path, and sometimes the issue is that the path goes backwards. Because from each cell we want to go to the predecessor. In general, we are interested in the path going from the start to the end. If we follow backwards and then reverse it, which is really what's being done with the recursion, okay, that gives us what we want. Any questions? So if we look at, and then I'll leave you with this, okay? Let's see if we had the example here. Kabunk, no. I want to look for one other thing here. Okay? Note that the edit sequence here, to convert thou shalt not into you should not, I said was a sequence of delete, substitute, match, and insert. What did it do? It started from the sequence. It deleted a character. It substituted the H for a Y. It then did a match, another match, and another match. And then what did it do? It inserted an O. It then substituted the A for a U. Does everybody see that? It then matched the L. It then substituted the T for a D. That was a substitute. And then it matched. Does everybody see that this sequence of operations described the way that you had converted one string into the other string? Okay? And you can find that by walking backwards from this cell. Any questions about it? How much time will it take if I give you this n by n, let's say I give you the n by m matrix for dynamic programming, and I want you to reconstruct what the path was once you have this matrix, converting that n character string into that m character string. How much time will it take to walk backwards through this matrix? Yes?
Is it O(n plus m)?
Okay. It is order n plus m, not n times m. Does everybody see that? Because from each step, we are going to be making progress either to the left or to the top or both. We have to travel a total of n plus m distance. Each step moves us at least one and possibly two Manhattan blocks towards where we're going. Okay? So this is interesting. Once we have completed the n by m matrix, reconstructing the path took time linear in the size of the path, not linear in the size of the matrix. Any questions about this or any questions about any of this dynamic programming stuff? Okay? Think, next problem, next class, think about the problem of the day. We're going to go through a couple more of these dynamic programming ones, and maybe you'll start to get the hang of it. Thanks for your attention. See you then.